We are live, I tell you. How are you all doing?
Good, good. Um,
Did
okay.
did you get any of the torrential weather that's been hitting all over the continent?
Nope, nope. We had some mild snow that is still on the ground, but it is so we've just been hovering around freezing, just a tiny little bit of
Ugh.
snow. It's mostly disappearing. Nope, nope. Our weather has been bland,
We
boring.
have amazing wind, like the kind of wind that's just like really cool to listen to when you know your house will not be blown out.
Yes.
And last night I was talking to somebody and I looked out the window because I saw motion and I caught my neighbor's wreath flip sideways, go bouncy, 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 snap off, and
Yeah.
get flung like a frisbee through their driveway. It was just sort of
Right.
like, wow, okay,
Yeah.
that's
Yeah.
wind.
When that wind get blows up,
Yeah.
then our power going out can't be far behind.
Oh
Like,
no.
yeah, every time. Like when there's big windstorms around, we just like start preparing for the power to go out. But now we've got the backup battery system, so
Yeah.
yeah, it can go out as much as it wants. I don't care.
Yeah. We've lived in this house a long time, and about 10 years ago, there was a significant power outage triggered by a transmission line
Mm,
set failing. And
yeah.
so we were out for like 3 days. And our
Ouch.
our
Yeah.
neighbors, who big powerful lawyer has since moved, was so annoyed by this that he wrote up everything and got all the signatures to put through to have the power lines on our, like, did a bond issue, like put everything through to get the power lines on our street buried, and it like
Nice.
drove up everyone's property taxes because it was a bond issue.
Yeah.
But at the same time, we were all like far too intimidated by the human who's like lawyer with name on side of building on Main
Yeah.
Street. So yeah, we just sucked it up with the property taxes, and our power only goes out now when the entire town goes out,
Mm,
which is a much better place
yeah.
to be.
I'd say my power goes out 10 times a year.
Oh yeah, ours does that too,
Yeah.
but no longer for multiple days.
Yeah. Yeah. Yeah, no, ours is always out for like maybe 6 hours.
Yeah.
When I used to live on this island, Hornby Island, the power would go out, and if it was late enough in the day, they'd be like, "We'll just get it in the morning." So, so you'd be out all night, right? You'd be out 18 hours was what you could expect. Sometimes it was multiple days, like bare minimum 18 hours. Usually, could easily stretch into multiple days. I think my parents' power had been out like 3 or 4 days when there was like
Oh
a really bad
jeez.
snowstorm and everybody's power was going out, and
Yeah.
he was under 4 feet of snow. It was a nightmare. All right, we should do our job.
We should. We should. All right. I need to start up the audio file, which means it's going to ask me to start it with a name. And we are
Oh, you know what? I
776.
gotta, I gotta hold on. Give me 1 second. I gotta rewrite something.
Okay.
Uh,
While he's writing, I want to share that this mug that is almost as big as my head and brings me all sorts of joy was made by Amy Davis Roth, Surly Amy, and she has a sale and she's been making mugs galore. Check out her store, look up Surly Amy Ceramics. Yes, I am plugging somebody else's stuff because this mug is my favorite thing, and you see it, and Amy deserves to have more people buy her mugs.
there you go. All right, I'm ready to press record.
Okay. I am pressing record there. I am finding the record button. I have pressed record there. We are recording in all of the places.
Astronomy Cast, episode 777, The Eddington Limit. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain. I'm the publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of Cosmic Quest. Hey, Pamela, how you doing?
I am doing well. The howling wind is tremendous. If you hear what sounds like ghosts in the background, that is the wind, people. Right. That is the wind.
Now, as usual, I can't hear it because we use Zoom to record, and the modern technology has made it so when your dogs are barking, I don't hear it, and so I'm definitely not going to hear the wind. But here we are. Now, I'm going to do something kind of mean, but it's for the best, and that is I'm going to say nice things about you, and you're just going to have to take it. Which is, I think a lot of people, when they reach out to us about Astronomy Cast and they talk about like our scripts and sort of how we prepare, they don't realize that there is no script, that this is entirely off of the top of our heads.
Yeah.
That I go in, and what's nice is for me, I don't really even have to prepare at all. I write the intro, which is sort of like my token donation to the cause. And I usually come up with the idea, but often Pamela has ideas that she wants to express. But then she has to prepare. And she doesn't have to prepare just for whatever is going to be the script. She literally has to prepare for anything that I might ask. And I don't know what I'm going to ask. So how can she know what I'm going to ask? And so, Pamela, you are amazing for being able to gather and prepare so much information. Be ready, sort of on your toes, nimble on your toes, to handle whatever comes your way. And in this case, there's going to be a lot of information about the Eddington Limit. And I don't know what I'm going to talk about. You don't know what I'm going to talk about.
It's true.
You don't know what you're going to talk about. And yet you were always poised and prepared. So amazing job. Thank you.
Thank you. This is a favorite topic, so hopefully I will not disappoint.
Great. Okay. How big can a star get? This is a calculation made by one of the original pioneers of modern astronomy, Sir Arthur Eddington, and it's named after him, the Eddington Limit. Now, astronomers are finding examples of giant black holes early in the universe, calling into question some of Eddington's assumptions. Let's explore this fascinating concept. And it's time for a break. And we're back. Okay, so the Eddington Limit. What is this calculation that Eddington came up with? So
back in circa 1916, that's when the paper came out. So he'd been working on this before. Yeah, this is fairly modern, but not so modern, because at this point in the history of astronomy, we didn't actually know how stars worked. People had realized they weren't burning coal, or they hadn't figured out galaxies existed yet. Eddington was trying, like so many other people, to figure out what it was that allowed stars to exist. And we were at a point in geology and paleontology that we were also realizing planet is old. And so that meant the star had to be old. That meant stars had to be burning for a long period of time. And they still hadn't fully figured out all the ins and outs of nuclear fusion. But Eddington started to propose, okay, so what if we have nuclear something going on in the center of a star?
Not coal.
Correct.
Yeah,
correct.
People were perhaps assuming,
would. It wasn't any kind of chemical exothermic reaction. They knew that much. It had to be something else, and we were starting to understand nuclear reactions at this point. And so what he proposed was something was going on, and we were really struggling to figure it out because electrons were like, no, we won't allow this. And so they had to figure out electron tunneling and quantum mechanics and stuff like that. So before we even fully understood the quantum mechanics that would allow the center of a star to do the things it needs to do, Eddington proposed, what if stars are balanced between light pressure pushing outwards and gravity pushing inwards.
Right. And like light pushing? Are you mad?
It was absolutely amazing. And I mean, it's more complicated than that. We have to look at what are the electron pressures involved, what are all the other chemical reactions, not chemical, what are all the other atomic reactions involved? And we're still working to figure out the details of stars. And in coming up with this idea, it was realized, well, shoot, if a star is producing too much light, it's going to overcome gravity and just blow things apart.
Right.
If anything is producing too much light, it's just going to blow things apart. So there is some kind of a limit on how much energy can be presented while at the same time gravity is trying to hold things together.
And this idea, I mean, I think even now, you know, we look at stars, we know they're in hydrostatic equilibrium,
Yeah.
and you say, well, yeah, it's the light pressure that is keeping the star from folding in on itself. Explain that idea of just like even the light pressure.
I love this. And if you ever want to see beautifully, cleanly done maths on this, Chandrasekhar put together a stellar evolution book that was published, I want to say in the 1930s or 40s. And there's copies of it still floating around. It's a little penguin book, Penguin Publishers. And the maths for this is entirely straightforward. It is all algebra. And so the idea is light it doesn't have mass, but it has energy. And energy in motion has momentum. And
Right.
so when photons hit things, they transfer momentum. And so every time you zot something with a photon, it can absorb the photon, and it also has a transfer of momentum in the process. And so in the core of a star, we have all of these nuclear reactions taking place. And in the process, photons are being produced. These photons work their way outwards, and they random walk. They're transferring energy in all directions as they go, which is good because that random walk without any specific direction supports a sphere quite nicely. And because they can escape outwards, you end up with the bulk of the motion on average being outwards, balanced against gravity. So in the center, you have this radiation pressure. It goes out. Then you have convective zones that are supported through the old-fashioned pressure laws and all these different things. You can just work through the math for each area of the star, figuring out where do these different pressures end up dominating. And this is actually like an undergraduate homework assignment that I still remember both
Right.
hating doing and really enjoying the fact that I was capable of doing it without getting help.
But that idea, I mean, I think when you think about, say, steam rising or filling up a balloon, and you sort of think about the sort of thermodynamic, the movement of the
Yeah.
molecules bouncing into each other, that would probably, and people were probably examining this
Yeah.
at the time, and that was probably their first instinct. Well, it's a giant blob of gas, and the gas is hot, and
Yeah.
here's how much sort of entropy is going on. We'll use that to calculate the star. But no, Eddington said, no, it's the light, it's the photons, not just particles bouncing into each other in the way we experience this in steam engines and things like that.
And what's wild is it takes all of these things working together. So the light is heating the gas, there's gas pressure added. So you have light pressure, you have light transferring heat, creating gas pressure. You have different atomic reactions going on, which are ionizing things and creating an electron pressure. And the classical Eddington didn't include all the electrons properly. And so we've had to modify the equations over the years to better and better represent what's going on in stars. It's super complicated, but Eddington was the first person to really realize what was going on. And this is where having Chandrasekhar coming and being his graduate student made so much sense. Between the two of them, they were able to figure out, and Chandrasekhar did surpass his advisor, and this did lead to a great deal of chaos that we talked about in our episode about Chandrasekhar years ago. But the two of them together were able to explain all the different phases in a star's life and what keeps stars going the way they're going. And for those of you watching the video, and Rich, please edit this out. My hair just spontaneously decided it's going to completely come down and there's nothing I can do about it. So
As long as it doesn't go in your mic.
Yeah, the mic is over here. I'm not wearing it.
We're going to continue this conversation, but it's time for another break.
Yes.
And we're back. So, okay. So this is kind of the limit, this hydrostatic equilibrium, but it also sort of defines how quickly a star can accrete mass to grow.
Yes.
So sort of help me understand this.
So what you end up with is as stars get more and more massive, it puts more and more pressure on the center of the star, which accelerates the rate at which light is being produced. At a certain point, the light pressure exceeds the gravitational force holding the star together. And so the light pushing outwards starts to push at a rate greater than what gravity can pull inwards. It's this balancing of forces that allows a star to start to blow things apart. It's the slow-mo version of what happens in a supernova. In a supernova, the star's core stops producing light. You run out of balance. It collapses violently. In the collapse, you end up with new nuclear reactions going on, releasing energy, and that blasts what's falling inwards, outwards. It's a much slower process, or at least a much less violent process that goes on in young stars, in massive stars, as material tries to fall into them. But it's the exact same physics. And I love the fact that we're dealing with the same equations, just implemented in different limits for all these different cases.
So then where does this kind of get us in the limits of how big stars can get?
This is where we keep being like, oh shoot, our observations don't match our equations. So we keep finding new ways that stars find to produce things that generate pressure and don't create pressure. So we think that the limits are somewhere below 200 solar masses. And I'm going to put it that vaguely because the universe likes to keep going, no, you were wrong. I'm going to make bigger stars.
Yeah. How about this star over here?
Yeah. And quantum mechanics is incomplete. We know this because particles don't do what we thought they were supposed to do. We don't know the underlying physics to the standard model. We just know the standard model is. There may not even be underlying physics, which is super annoying to think about. But at some point below 200 solar masses, you are adding material to a star and it just starts blasting light to the point that it clears the area around it.
And is that sort of separate? Like I think about the Eddington limit core first, that you're kind of imagining that you're adding material to the star is getting hotter both in its core and at its surface. And like the level of heat is kind of ridiculous. Like say a star like our sun, 30 million at the Kelvin, I think at the center, while say 5,800 Kelvin at the surface. But you take a star, like the hottest star, like one of those like 200 times solar masses, and you're at millions of degrees even on the surface. I mean, they're ludicrous.
Yeah.
And so if you try to add more material, then this thing is going to, its age will decrease and it's going to go through some of its phases of dying almost instantly, right? Because it's just, but then I think where you're getting at next is that not only that, but then you have all of the incredibly intense solar wind that's coming out, all of the radiation that's coming off of the star. This is heating up the gas that's around it. You need cold gas to get a star to form, not
Yeah,
hot gas. But the brightest
exactly.
stars heat up the gas. They make ionized gas, and then that doesn't want to add to the star. So in addition to sort of the internal limits of how big a star can get, you also have its sort of interaction with its environment, preventing additional material from falling in.
And And this is just one of the many super cool things that happens as we literally live in the realm where we're looking at the quantum mechanics of how atoms change as a function of temperature, pressure, and it, everything is balanced between these things. Temperature and pressure defines all these characteristics, and the pressure is coming both from gravity inwards and light outwards, but some of the energy can go into ionization, and this starts to lead to really weird things. And I'm going to take a moment and say variable stars. We have to remember the variable stars, because one of the super cool things that Eddington realized while doing this work is in a star's atmosphere, you have light going through all these different parts of the star that are at different temperatures, different pressures. And because of this, they have gases at different states. And gases in different states have different optical properties. And one of the weird ones is helium. So helium 1, light goes through it. So neutral helium, light goes through it. Helium 2, helium with no electrons attached, is like, I shall not let light pass.
Hmm.
And opacity means that when the photons hit a cloud of fully ionized hydrogen, it is more likely to cause pressure instead of to pass through. It acts like a wall.
Right.
So in a star, as it heats up, it hits a point as it's heating up, that the helium goes from singly ionized to doubly ionized, and it becomes opaque. And it's like, I'm going to expand instead of getting hotter at this point. And so you have a star's atmosphere starts expanding instead of heating up the same way. Now, as gas expands, it cools. So as the star is expanding, it eventually hits the point where it's like, I'm going to become singly ionized again. And then the light can just pass right back through. And so now you have a star that doesn't have the same amount of light pressure because it's now singly ionized helium. And it's also cooler. And so there's less light pressure in general. And so it begins to collapse. As it collapses, it heats up.
Hmm.
And it eventually hits the point where it heats up enough where it starts to expand because it's heating, but it's also heating faster than it's expanding until it hits that doubly ionized helium again. This is the kappa mechanism, and it's entirely driven by quantum mechanics playing an extra role with the ionization of helium. So it's the little physics like this where things decide, instead of cooling, expanding, heating, they're going to ionize and just do something completely different with all that energy. These are the kinds of things that we keep realizing we've left something out of our
Right.
equations, and this is why stars can be bigger and stuff like that.
You just tucked a mini episode about variable stars into this
I
episode.
did.
Nice
I
work.
hid
Yeah.
variable
Yeah.
stars in the
No,
episode.
that's amazing. All right. We're going to talk about the implications of all of this in a second, but it's time for another break. And Rich, I said like 30 million degrees Celsius. It's actually 15 million Celsius. The interior temperature of the sun is 15 million Celsius.
And everyone on YouTube who's commenting on how well my hair matches the nebula, it's because my hair is currently green screening. My hair was up because it has faded to green from blue, and I haven't re-dyed it yet. I'm procrastinating as long as possible, and I think today is the day that I'm going to go bleach my hair.
Once your hair is matching your green screen,
Yeah, you can see the
it's time.
stars through my hair
Yeah.
right now as
Yeah.
I move.
That's awesome.
Yeah.
And we're back. So now I think we need to kind of pull this all together, which is when you take this law, this limit,
Yeah.
and you use this to calculate how stars grow in the early universe, and then you can kind of apply this to the growth of black holes, you get a certain sort of limit for how big a black hole should be.
And to be clear, the limit is not the feeding of the black hole. The limit is the accretion disk around the black hole.
Which acts like a star.
And
Yes.
so you can sneak up on bigger and bigger black holes, but it's trickstery. So the situation that we're looking at is take black hole. This works for stellar mass black holes. This works for supermassive black holes. It does not matter what size black hole you have. When the black hole is feeding, because angular momentum is a insert naughty word here, as material attempts to fly in towards that black hole, the angular momentum is like, no, you shall go spiraling around. And so material builds up in a disk of spiraling material that is trying to shed its angular momentum through friction and light and other forces.
And how this works is still a bit of a mystery.
It's a good homework equation. Another thing I've really enjoyed, but this is a graduate school homework equation.
Right. But how this, yeah. I mean, just like how you can get material and how you can get, say, black holes to merge is still a bit, this sort of
shutting all of the momentum is this is where gravity waves. You're now getting rid of energy through gravitation instead. It's super cool.
Yeah.
I love this part of physics. So you have your black hole, you have an accretion disk around it. And as the material builds up in the accretion disk, it gets thicker and denser and has super high pressure. And temperature and pressure are the two things you need to have that are high in order for nuclear reactions to start occurring.
Right.
And it's not identical physics to what's happening in stars, other than like it's nuclear reactions the same way, but you're not going to get like the CNO cycle that is working in the same ways in an accretion disk. It's slightly different,
right,
but also the same physics.
Right.
Yeah.
But your point is that this disk around a black hole
generates light.
Gas is being mushed together and the temperature is increasing and it's starting to behave like the interior of a star, falls under the Eddington limit. Time to calculate how big these accretion disks can be around various black holes before they're too hot. They start to blow themselves apart. The same physics is happening in this situation.
And with supermassive black holes, the ones in the hearts of galaxies that like to be what we call quasars and active galactic nuclei, once you start hitting the quasar side of that equation, the black holes can have accretion disks so large that they start generating light pressures that empty out the cores of galaxies.
Right.
At which point, there's nothing there for the black hole to eat anymore. So it chows down on that accretion disk and then sits there going, I am starving. There is nothing I can do about this. I have done this to myself.
But so then the math, when you sort of think about it, is like you start at the very beginning. You say, okay, we got the primordial hydrogen and helium.
Yeah.
We know how big a star can get. So let's calculate the first stars. Great. That tells us the stars. Let's say those leave behind black holes. Great. Now we know how big those black holes were. Now those black holes try to pull in mass.
And I need to put numbers on this because we are starting to realize that these first stars could have been between 1,000 and 10,000 solar masses.
Well, hold on, because now you're hold on. I'm trying to follow like the standard line here, and then
so
obviously
standard
we
line
break the rules.
is not the first stars. The second generation of stars.
But
He's talking about the second.
But even the first stars, like you've got hot cores. They're going to, you're going to reach a limit, how big the star can get.
Yeah.
Maybe it can get bigger because it has less metal that's poisoning it or whatever. But anyway, so then you get those first stars die, you get black holes remnants, the black holes feed, the black holes get accretion disks. You're limited by how big the black holes can get. And so that defines how rapidly these black holes can add on mass. Their accretion disks get bigger, then they can feed faster. Yeah. There is a limit. Yeah. And the astronomers have gone back and they've made all these calculations, string them together. They've reached the sort of the size of the black hole that you should expect at certain ages of the universe. And the problem is the ones that we see are too big.
Yes.
Too massive.
Yes.
That they broke the rules.
Yes.
that at some point they either violated the Eddington limit in terms of stars or they violated the Eddington limit in terms of black holes. But now we're in we live in a universe with black holes that at some point took Eddington's careful calculations, tore them up, stomped on them, and said, "Ha."
Or they just found another process. I mean,
Right. And so now, please, let's go through where we think the universe has potentially violated the Eddington limit.
So, and the Eddington limit is limited to this is what happens when gas is doing the infalling. And it's because light pressure can push on gas, but light pressure pushing on bigger objects is going than atoms and gas particles and dust particles is going to have a different kind of effect. So when you start looking at two black holes merging together, the Eddington limit plays a different kind of role. And also with accretion disks, if you look at the situation of supermassive black hole feeding on the gas and dust around it, empties its area. Now, you merge two galaxies together, you rearrange where all the dust and gas is, and you get to start over. Now, where we start running into problems is we expect all of these things to have time scales. And the time scales are like, nope, you haven't had enough time in the universe. And we keep finding this over and over and over. So we need to figure out how to reset the time that it takes for things to happen to be different. And this is where like new research just in the past few months, I think, time has no meaning. It still has no meaning.
Yeah.
Is starting to point towards the first generation of stars were far more massive than we had envisioned. And they're actually starting to come out with, well, if you make it this big, you get this chemical ratio. And we actually see nebulae filled with that chemical ratio exactly as expected at less than a billion years of the universe being in existence.
Right. And so it might be that if you have that first star, just hydrogen, helium, no metals, they're able to get much bigger.
We know that is true. And it's true because you don't have all the additional lines that electrons can go into to change how light is held back. You end up with a lot more of this helium being its opaque self, allowing stars to just get big and hot and stuff like that.
And like you mentioned some recent research, and there has been examples of observations that have been made with X-ray observatories and things like that, where they're literally watching black holes feed at super-Eddington rates.
And that we're still trying to figure out. What did we miss? And this is where we're starting to realize, oh shoot, you have to include electrons in ways that we didn't originally. You have to include what is the chemical constituency of the accretion disk in ways that we hadn't thought of before.
Yeah, magnetic fields.
Yeah. So you have to balance every single force. You have to balance every single quantum reaction. And trying to figure out what did we forget, this is where creativity is a part of science that we don't acknowledge nearly enough, because it's one thing to go through and do our homework where we're like, let's just worry about what hydrogen and helium are doing. They're the bulk of the universe. And then you start realizing, okay, so to explain stars like our sun, you have to start including heavier atoms. Otherwise, it doesn't work at the mass it's at. Okay. And so we're getting more and more complex in a lot of cases, but the computer power and also the creativity of the person running all of the maths sometimes means we just don't think of things, or our computers aren't powerful enough for us to include all those things. Both factors are at play. There are a lot of times where you're like, shoot, if I run this the way I have it written, it's going to take 4 months. So let's simplify the equations. And then there's also the human willingness of, well, I could figure out all of those atomic quantum mechanic electrons bouncing around doing their thing, and I do not want to. So I'm going to simplify. I'm going to do this in 1 dimension instead of 3 dimensions. There's so many ways that we simplify things because that makes the math doable. And there's so many ways that we simplify things because we don't have computational power yet.
Yeah.
Both
But you
affect us.
you sort of hold that the most complicated field of science is
Hydrodynamics.
plasma dynamics,
Yeah, yeah.
right?
And that's
That
exactly what this is.
and this is
It's
one of those problems that you have magnetic fields, you have plasma, you have moving
charged
fluids,
particles.
charged particles
Yeah.
moving like a fluid in this environment, and it is one of the most complicated things. And then it also brings aspects of general relativity, and also
Yes.
brings on a whole bunch of
Yeah.
quantum mechanics. What I love about this though is that it's kind of like, when you're like doing homework assignments, you've got some complicated problem that you're trying to do,
Yeah.
and you do your math, and then but you know the answer. You go and you look at the answer key, but it just gives you one number. It just says 45 meters per second, and you go back at your calculation, you got 31 meters per second. You're like,
Yeah.
where did I
Yeah.
go wrong? And then you examine every single part of the calculation to get you to go, like, I know what the answer has to be, and so I have to sort of revisit all of my assumptions and
Yeah.
try and figure this out. The universe has told us what the reality is. The Eddington limit works very well most of the time, and yet we live in this universe that is slightly different. And so it's those assumptions somewhere that we're off track, and but you're not just like completely moving in an area where you have no idea where you're going.
And
So
what
it has
what's
structure.
what's so amazing about this is when Eddington first did this, when Chandrasekhar expanded on this, when I did it as a homework assignment, we were looking at a line through a star from the center to the surface, looking for all of the places where changes in pressure and temperature changed what physics was dominant. So in the core, you have nuclear reactions. At what point, as you move away from the core, does the pressure and temperature hit a limit where you switch from one mode to the next?
Mm.
It's a straight line calculation through a star, and it's good enough. As we now look at accretion disks around supermassive black holes, we're still largely trying to figure out how to do it by taking a cut through that disk, looking both up and down and also center outwards. So now it's 2 dimensions. We're still simplifying. And now, because of all the rotations and because of everything else, it's no longer something you can do with pen and paper. We have gone from 1916 working on a chalkboard to 2020s working on a supercomputer, and it's the exact same physics. We're just changing where we're applying it.
Yeah. Well, it's a fascinating concept, and I think we're going to see a lot of work. And thanks to James Webb and other big observatories, we're making a lot of progress. So stay tuned for maybe someone coming up with the answer. Thanks, Pamela.
Thank you, Fraser. And thank you so much to everyone out there on Patreon who allows us to keep this show going. Rich is able to make us sound good. Aviva is able to keep the website updated. Everything works because of you. This week, I would like to thank, and this is where Rich puts the names.
All right. Thanks, everyone. And we will see you all next week.
Bye-bye, everyone.
Unless next week is when you're taking your break.
No, next week I'm still here. So,
okay.
As a reminder to everyone, including Fraser, I'm working through the holidays because that's just what I generally do. And a group of us are going on a group vacation because we couldn't afford airplane tickets to all be in one place for either Thanksgiving or Christmas.
Yeah, it's madness.
And so instead, we managed to pool resources in the best of possible ways, where between different people's frequent flyer points and hotel points and everything else, we're all going to Florida for a week, and it's actually affordable. And so Martin Luther King Monday, which is January 19th, I will not be here. I am instead going to be probably at Animal Kingdom Lodge for lunch because you can book lunch without having to have park tickets. And the plan is I'm going to be with a group of people that I only know because of Astronomy Cast and who have become my bestest of friends. I'm going to be drinking and eating bread dipped in sauces while looking at animals wearing flannel pants. This is my plan for January 19th.
That sounds great. All right. Let's get into the questions that people have.
And I'm just going to be watching my hair green screen because it amuses me.
I can't see it. I just see sort of gray hair and purple hair. Let me see. What colors am I seeing here? Yeah, sort of like a little bit of purple, a little bit of green, blue, and a little bit of gray.
Yeah, it's just totally green screening, and I have a different background on our recording, so there's actually stars in it, and the stars are shining through.
All right, so go ahead and put any questions that you might have into the YouTube chat. So I have been sort of going through my legacy media.
Sorry, I'm laughing at who wrote this. Zapfan put helium-2 is Gandalf. Thou shalt not pass.
Yeah, so that's what reminded me. So I finished watching
of laughter here.
The Lord of the Rings extended editions, all 3 movies with my wife. And so we would put one disc on each night. And so it took us 6 nights to get through the whole thing. And it totally holds up. There's some of the special effects is a little mediocre. There's some scenes like the classic where Legolas like jumps on the back of some moving animal and you're just like, oh, cringe. But most of it is good. And just the pacing and all of that is terrific. And then for the last 3 nights, we rewatched the Matrix series.
Oh, I love that series.
Yeah. So Matrix Reloaded, and Matrix Revolutions.
I don't know. And
and I think a lot of people, like Matrix Reloaded was great. I really enjoyed it. Like Matrix is obviously, top in my top 10 of all time. And I watch it and you watch the first 5 minutes of it and you're like, oh no, it's totally cringe. There's like a couple of really bad effects where Trinity is like jumping through a window and she kind of spins through the air before she goes through the window. And it just looks awful. And then that kind of classic where she kind of jumps up and she's like got her feet and then she kind of kicks 2 people. It's terrible. But that's it. And then the rest of the movie, the special effects holds up. The action sequences are really good. And the rest of the movie is terrific. And then Matrix Reloaded, it is just top notch beginning to end. I think, they get into this kind of weird philosophical muck, which is a problem. The third movie, again, just solid, beginning to almost end. And then the end fumbles so hard that it leaves this poor taste in your mouth for the entire movie and the entire series. And I think a lot of people, they watch the end of the third movie and they're like, that's your ending. And then they then went back and it's kind of like my experience with Lost.
Yeah,
Battlestar Galactica.
Battlestar Galactica is the one that did it to me.
Battlestar Galactica's ending is unforgivable to me.
Yes.
And so I can't even I remember watching the first season, the first episode of Battlestar Galactica. It was so good. And then it doesn't matter. It is ruined. And so same thing with Lost. Lost is unwatchable. Like if you said let's watch Lost, I'm like, let's just, pound nails into our hands. No, thank you.
Fifth Element stands up. Go watch Fifth Element now.
Totally. Yeah. Fifth Element I think that's like my wife. That's when my wife and I like knew we were in love. She was like, do you like the Fifth Element? I'm like, oh, I love the Fifth Element. She's like, it's my favorite movie. I'm like, tell me more. So yeah. So anyway, so that's it. So that's where I'm at now. And I'm sort of continuing my journey through the sort of, and I love to be at this point. Like I was watching Matrix Revolutions. Yeah. And I didn't know what was going to happen. Like it was a very weird, like it had been so long.
It's been enough years. Yeah.
Yeah, it's been so long where I just didn't know what was going to happen. Like rewatching, say, Deep Space Nine, and like I don't remember this episode. I don't remember what's going to happen. Yeah, I love that. I love that where you have a show that was so influential to you and you loved it so much, and then you watch it again and you're like, oh my God, I don't remember all the details of this. This is
Yeah.
not me retreading
Yeah.
familiar ground. This is me watching
Re-experiencing it for the
something,
first time. Yeah.
experiencing it for the first time. Yeah, you get that little hint.
But
You
you
know,
also spot more Easter eggs. Like
yes.
there is, just because I've lived more life since I first watched it, there's like the stupidest Easter egg. Okay, me, I'm always bad with names. This is who I am as a person. I'm terrible with names. The I want to say it, her name begins with an L. The second telepath that comes on, the one who ends up being like super powerful. When she
In which show?
in Babylon 5.
The telepath in Babylon 5.
The not the first one, the second one
Right.
with the
The
red hair.
red-haired one. Yeah. Yeah.
So
Anyway,
it
okay. I
begins with
forget.
the letter L. That's all I
Yeah, I
remember.
think you're right. Yeah. But now I'm
But
thinking of the doggo play, the person who fell in love with Rom in Deep Space Nine. But anyway,
no,
please continue.
so I when she's setting up her apartment, she like people come to check on her, and she's sitting on the floor in the middle of all of this chaos, and there's an IKEA bag sitting there. And it is the most wonderful Easter egg. Like, it's that classic
Of course, they still have a
blue.
Kia.
Right.
Yeah.
And when I first watched the series, I had never been to an IKEA. And so just catching that Easter egg, because I had lived more life, is one of those things that
Yeah.
brings me stupid joy. And it's like some of the things that you see that she's unpacked are things you can still go buy at IKEA, and I love it.
Yeah, that when they're well, for me, that when you're watching Babylon 5, it's the newspaper universe today,
Yes. Yeah.
which is always funny. I promise I did not steal the name. I came to it independently.
Lita, the audience came
Yeah,
through
there you
for
go.
us. Her name is
Thanks.
Lita.
Yeah,
Thank
we
you.
were there. It was like Lyra Lee. Yeah, all right. Okay, let's get into some questions. So Hal
Okay.
McKinney asks, is it expected that all galaxies will collapse into its own supermassive black hole galaxy center?
No.
No.
There is no reason for all of the stars and everything to lose their momentum
Yeah.
and spiral in. Now, if it turns out protons can decay, sure. If we end up with runaway expansion of the universe, everything is just going to become a fog of energy and be torn apart. So there's that to look forward to.
Yeah.
But you have to have a reason for things to come out of the orbits they're in. Black holes don't magically just reach out and go, I'm going to eat you now.
Yeah.
There has to be an instability to drive.
So, like, when you think about kind of like deep time,
Yeah.
like 10 to the power of, like, not proton decay, not black holes evaporate deep time, but still a long time,
Yeah.
you're going to get a lot of three-body interactions from stars going past each other and stars interacting with and then interacting with the black hole. But you're not necessarily going to get them going into the black hole. You're going to get them getting kicked out. It's a small target to hit even a supermassive black hole.
Yeah. So those three-body interactions will cause some things to go in. They will cause more things to go out. But if you're far enough from the core, you're just going to live out there going, hi, I'm a white dwarf. I'm just going to collapse down into being a diamond now if I'm a carbon white dwarf.
And just orbit forever.
Yeah. Yeah.
Yep.
And that's fine.
Arjun asks, would the Eddington limit change in the early universe for some reason? I mean, I think we already kind of covered one, which is just that stars being made out of just hydrogen and helium, that gives you, but not like the fundamental.
The physics doesn't change.
Right.
It's the composition of stars require different quantum mechanics to be considered. And by different quantum mechanics, I mean a different suite of atoms are involved in the equations. When you only have hydrogen and helium, stars can effectively cool, they can't effectively radiate their energy, and they end up much, much larger in what they can support.
Right. Roger Luther asks, an article came out last week on New Scientist about stars with black holes as that with their cores may exist. What are your thoughts on this?
I haven't read the paper yet. I saw the headline and I went, oh no. Mm-hmm. So my current reaction is, oh no, heavy sigh. I need to read the paper. I'm pretty sure
Right.
something got lost in translation somewhere. Because
Yeah. So
spherical, I mean, like a disk of material, sure, but I don't know how you get a sphere of material around a black hole.
right. And like New Scientist is legit.
Yeah.
And so my guess is that they have reported on in a paper
Yeah.
in a journal or on archive, which is sort of that's how Universe Today operates.
Yeah.
And so I think you're exactly right that if you're going to have a black hole that is produced in the kind of stellar way, then you're going to have something that is 3, 5, 8 times more massive than the sun. You put that in the middle of a star and it wrecks that star
Yeah,
pretty
exactly.
promptly.
Yes.
But you get a primordial black hole, something with maybe the mass of a mountain or something, some kind of three-body interaction plops it into the middle of a star,
Yeah. I mean,
then that is,
microscopic black holes kind of don't count for articles like this because you can stick them anywhere and they just go there going, I'm tiny.
yeah,
I'll
yeah,
eat something every few hundred years, but I'm too tiny to do anything
yeah.
more dangerous.
And that what you get is heat,
Yeah.
excess heat in the interior of the star. And so you might be able to tell that a star has a microscopic black hole inside of it because the star is giving off more heat than you would expect for its size. And this has also been proposed for dark matter being inside stars, that dark matter, if it gets trapped inside stars, can annihilate, can produce additional heat, makes the star hotter. Maybe even planets could be hotter, and that a
Yeah.
way you could sort of detect the presence of things inside stars like this is if there's like an excess of heat.
And this is where it all comes down to what have we not included in our equations? What are we not creative enough? What do we not have the technological know-how? Or what do we just not know the quantum mechanical properties of? That's the thing about dark matter
Yeah.
is we know some of the properties, like we know the cross section for collisions because we can measure that from X-rays, but we don't know other quantum mechanical properties of dark matter until we know, are they axions? Are they sterile neutrinos? Are they something we haven't thought of yet?
Yeah.
Yeah,
Yes.
we just don't know.
Those are all the questions that I've got on YouTube. Do you have any questions?
Hold on. I have snark. Do not overfeed your pet microscopic black hole, especially after midnight. I love these. I love comments like this. The Twitch chat brings me joy. Okay, weird question from RenanGeo06. Why do stars with high metal? Okay, why can't stars with high metallicity be that big as stars with lower metallicity? Does that mean that the universe age and the level of metallicity increase the stars as? Sorry, trying to translate. Does that mean that as the universe ages, the level of level of metallicity increases, the stars formed will be different than the ones today? So the very first generation of stars lived and died very, very quickly. And because massive stars form faster than tiny stars, it doesn't look like tiny stars made of only hydrogen and helium had the opportunity to form. So the most massive stars that formed first died super fast and died before tiny stars could form, filled the universe with heavier elements. Thank be. So those first stars that were purely hydrogen and helium, yes, they were significantly bigger. And yes, stars with different metallicities can have different sizes, but once you have metals of any kind, the changes are minor and can be ignored to first order. You include them when you're trying to calculate like the ages of globular clusters looking at a color magnitude diagram, because it turns out you can like look to see which stars have stopped burning hydrogen and started burning helium and other elements in their cores and figure out the age of a globular cluster, but there's just enough difference that you do want to include metallicity or you end up with globular clusters older than the universe, which is wrong.
Right.
So yeah, we do include them for some calculations because they do introduce changes, but the changes are minor enough that to first order homework assignments for undergrads, you ignore them.
Any other questions?
Let me scroll further.
Or snarky comments?
I do love the snarky comments. We have two people, Pinky and the Brain, that just say hi to each other, and that brings me joy. Another black holes have arms like T-Rexes. They'll eat you if you get close, but can't reach out and grab you. It's true.
I think that's exactly.
Yeah.
I always say black holes aren't vacuum cleaners.
Yeah.
And that of course, if you replace the sun with a black hole, the solar system would continue on with the same mass. The
Everything
solar
would
system
be
would
very
just continue on. Yeah, everything would get cold, but the solar system would just continue on in its exact orbits. And now you wouldn't have the future complexity of a dying sun. So
it's true.
Yeah,
it's true.
Yeah, you would be freezing the solar system into eternity.
I probably didn't reread. I read for the first time Arthur C. Clarke's The Star, which is the darkest friggin' Christmas story ever written.
It's a Christmas story? I haven't read that.
It's a Christmas story, but it is so dark that like I wanted to put out a narration of a good sci-fi story to the folks on my personal Patreon. And I read that one and I'm like, this is not something you read going into Christmas. It is because Arthur C. Clarke was adamant atheist where he felt that science could remove faith and wrote a story designed to aid and abet in that. And one of the premises of this was you can see signs of a star getting ready to basically head into supernovae. And so a civilization that had the capability to travel around their solar system could put a monument to their civilization all the way out at the edge of the solar system where it would hopefully survive while their inner world was destroyed. And one of the things that made me so sad about this story is some of the basic concepts have changed so much since the 1950s to today that in talking about this story, I had to start with, okay, so here's all that's wrong with the physics.
Right. Yeah.
Now let's look at the story.
Yeah.
But don't read The Star if like you don't want to be devastated. But if you do feel like being devastated, I have a narration of it up on patreon.com/starstrider.
That's amazing. Yeah. I don't want to spoil it. I just spoiled myself. I checked on Wikipedia to understand it and spoiled myself. But apparently it was a Christmas episode of The Twilight Zone in 1985.
Yeah. And
I didn't even know that.
They did change the ending ever so slightly so that the Twilight Zone episode wasn't as bleak as the actual story. Because the actual story is just like, and now I need to go drink.
Yeah.
But
that sounds great.
Yeah.
Awesome. Well, we've reached the end of our hour. So thank everybody for hanging out with us today. Thanks in advance to all of the people that Pamela thanked in the episode who are going to have to work on this nonsense and turn this into some kind of listenable, watchable material. We're sort of on a normal schedule. So I've got my live stream tonight at 5. I just published an interview. I'm doing an interview in like 30 minutes that I have to do.
I'm going to put together a That Takes Math Q&A.
Oh, that sounds great.
That I'm actually looking at the thermodynamics of data centers. I'm going to look at the thermodynamics of a single GPU just to show how ludicrous the idea of data centers on orbit is with...
Yes. Oh, yeah. Scott Manley did as well, but I think that's great. I think people are... looking at this and just going, the math doesn't
does
hold.
Not work. Yeah, I need to reach out to Phil Metzger and be like, dude, tell me why you look forward to these. I want to know his answer.
Right.
So yeah.
Awesome. All right. Well, thank you everyone. And we will see you all next time.
All right. And awkward transition. Bye-bye.